Good afternoon, everyone. Welcome back. Good morning,
Morning.
everyone. Welcome back. We're going to try and get you through your Monday morning. You can see it's a rough one for me. I'm Steve.
And I'm Scott.
And together we're Backyard Musings, the Science and Technology channel.
Yeah, we're talking about some material today and how they're going to use this material, or could they use this material, I guess. And it's pretty fascinating. Stronger than
structural steel.
Yeah, structural steel. So pretty amazing stuff here. So here we go.
A cobalt aluminum nanolaminate has shattered the usual trade-off between strength and flexibility, emerging up to 10 times stronger than structural steel without becoming dangerously brittle. So this is aluminum. Jet engines demand materials that can survive tremendous heat and force without bending, cracking, or slowly losing their shape. And the reason the jet engines need it, because you need light materials to get that plane off the ground.
With less fuel.
What?
With less fuel.
With less fuel, yeah. The strongest candidates, however, often come with major weakness. They're too brittle to deform safely. Would you like to know more?
Purdue University engineers have found, that's in your neck of the woods now, right? Michigan, right? It's in Michigan?
It's my law school alma mater.
Purdue, is that Michigan or is that Indiana?
No, that's Indiana.
Indiana, okay. Purdue University engineers have now found a way to overcome that trade-off in cobalt aluminum and an intermetallic compound with potential uses in high performance turbines. By redesigning the material at the nanoscale, the researchers created a form of cobalt aluminum which is COA, is that AI or A1? AL for aluminum, yeah. And that is exceptionally strong, but can still undergo substantial deformation at room temperature. So we can it's just flexible, it's soft and flexible, right? Is that what we're talking about?
It's strong.
Yeah, it's strong, right.
This advance, reported in Science Advances, could point toward a broader strategy for making notoriously brittle intermetallic compounds more practical for aerospace energy and defense technologies.
Intermetallics contains two or more metallic elements arranged in a highly ordered crystal structure. That atomic order can give them remarkable strength, high melting temperatures, and resistance to creep, the slow deformation that occurs when a material remains under stress for long periods.
So just me being a construction guy, asphalt, you ever see where you have asphalt ruts in the road because it's pushing? That's called creep also, the asphalt creep.
Yeah, okay. Or they pour asphalt and they don't get it sealed well, and then water will get in there and start pushing it apart.
That's alligator cracks.
Alligator cracks, right?
Yeah, the creep occurs from the tires, all that weight on the tires constantly pushing it aside. Right. No cracking involved.
Yeah, and and it's not maintained. You got to maintain it, right? You got to service it. So
these qualities are valuable in jet engines, gas turbines, energy storage systems, and automotive components. Yet the same ordered structures that make intermetallics strong can also prevent them from deforming easily. Instead of bending under force, many fracture, particularly at room temperature.
COAL illustrates this problem. The compound is strong enough to be considered for demanding turbine compounds or components, but its brittleness makes it difficult to manufacture into complex shapes and limits its ability to withstand sudden mechanical stress. The researchers approached the problem by deliberately introducing imperfections into the material. Okay.
In a crystal, atoms normally follow a repeating geometric pattern. A dislocation is a microscopic disruption in that pattern. Although defects are often associated with weakness, dislocations can give metals a way to change shape by allowing layers of atoms to move rather than break apart.
COAL typically lacks enough mobile dislocations to deform substantially at room temperature. Previous efforts to improve its plasticity by changing its composition or combining it with other materials had only limited success.
The Purdue team instead built dislocations directly into cobalt aluminum as it formed. They also created a network of amorphous interfaces, then thin boundaries, where atoms lack the ordered arrangement found in a crystal. Quote, in this study, we show that cobalt aluminum can exhibit significant plasticity at room temperature, offering a new alternative approach to improve the plastic deformation capability in cobalt aluminum, said Qi Zhu, a Purdue postdoctoral researcher and study's first author. These flexible internal boundaries act as more than passive separators. During deformation, parts of the interfaces crystallize and help generate additional dislocations, giving the surrounding cobalt aluminum layers more ways to absorb force.
The resulting nanolaminate reached a yield strength of 6, I don't know what that gigapascal, a stress measurement, roughly 6 to 10 times that of high strength structural steel. It's still staying flexible. Remember that. So that's pretty cool. Yield strength measures the amount of stress a material can endure before it begins to deform permanently. Despite that extreme strength, the material sustained 15% plastic strain under compression at room temperature. In other words, it can undergo significant permanent deformation without immediately fracturing.
The team produced the material using magnetron sputtering deposition. That's a very important technique. So remember that. Magnetron sputtering deposition.
Okay.
During this process, atoms are released from the source material and deposited as a thin film on another surface. Unlike conventional casting, which solidifies molten metal, sputtering allows the material to form directly from alloy vapor. That unconventional route helped trap large numbers of dislocations into the cobalt aluminum while creating the amorphous aluminum cobalt interfaces.
The researchers compressed the material while observing it inside a scanning electron microscope. This situation, right? Is that what that is?
In situ. In situ.
Oh, this in situ. What the heck is that?
That means in place.
Inside. Okay. Inside of play. Testing allowed them to track how the microscopic structure changed as the cobalt aluminum deformed.
Yeah. University of Houston professor Yashashree Kulkarni, not making that name up, and PhD student Anand Matthew. Shouldn't it be Matthew Anand? I don't know. Anand Matthew.
Don't judge.
Don't judge. Also perform molecular dynamics simulations to examine the process at the atomic level. Their model showed parts of the amorphous interfaces crystallizing under pressure and releasing dislocations into neighboring cobalt aluminum layers.
Together, the experiments and simulations suggest that the interfaces function as active sources of plastic deformation. Rather than weakening the material, they help it respond to stress without sacrificing its exceptional strength.
So the current material is a nanoscale layered system. So nanoscale, very, very, very small.
Yeah, one of Steve's very favorite things.
Produced through thin film deposition, not yet a bulk turbine component. The researchers' next challenge is to transfer the same structural concept into larger cobalt aluminum nanocomposites that could be manufactured at an industrial scale.
All right. If the approach works across other compounds, it could provide engineers with a new way to design materials for environments where conventional metals struggle. Instead of choosing between strength and deformability, researchers may be able to engineer both by controlling where defects form and how internal boundaries to respond to force.
Quote, ductile intermetallics will significantly boost our capabilities for designing advanced materials for aerospace and outer space energy, and defense applications, the author said. So pretty neat. I wonder if the folks at Dow are working on this here in Midland.
Yeah.
You know how we have teachers in Desert Knolls Ward? A lot of teachers. We've got a lot of chemical engineers in my ward.
Oh. Do they all get along?
Yes. They all carry periodic tables in their back pocket.
Do they have pocket protectors too?
They have pens that must be protected.
Okay. No. And in that pocket protector, do they have the slide rule?
No. They've got a fanny pack for that. Fanny pack.
Right. They've advanced to the Texas Instrument calculator.
Well, these guys are cool, man. They're cool.
That's good.
They're all right.
Yeah, I know how cool those engineers can be. My dad was an engineer.
They're smart.
They are. Yeah. So smart it'd give you a headache. So what else? So that means you got to be near some kind of a manufacturing or development facility.
Yeah. Dow Chemical.
Is that where you got the story? Did you sneak the story out of Dow Chemical?
No, out of Purdue.
They're not going to be knocking on your door, are you saying?
I'm going to send this. I'm going to forward this to
speak with you.
One of the guys in the Elders Quorum presidency, he's a chemical engineer. One in the bishopric is a retired chemical engineer. I think I'm going to send it to both of them.
Okay. There you go. All right.
Thanks for joining us, folks. We'll see you in the afternoon.
Take care.
In case you didn't know, we broadcast twice a day, 7 a.m., 1 p.m., Monday through Saturday.
Right. And we take Sunday off. Okay. Take care, everyone. Thanks. We'll see you this afternoon.